In the previous video, we have derived the key properties of the real exponent. We showed that it is well defined and what it means to take a real exponent of a positive real number. We've also derived key properties of exponents that we are going to use and the limits that we are going to quote. In addition, in also previous video in this playlist, we have established the limit when the value of x here is 1. That is, we show that 1 plus 1 over n to the power of n, as n tends to infinity, that limit exists. We actually show that this is less than 3, and we call this limit by the letter e, which is the Euler number, right? This is the natural base of the logarithm, and now we're going to prove this result. Okay, so what we'll use from the previous lecture is mainly this main result, this main property, which even at the best courses at top university, this result is often omitted or given as granted and not proved rigorously. And in the previous video, which was very technical, we have proved this result rigorously and established the meaning of what it means to take the real exponent of a positive real number. So we will be relying on this result, which is essential to proving this. Okay, so the first proposition that we're going to prove that now for any sequence of real numbers, alpha n, which is non-zero for every value which tends to infinity, then this limit exists and this is the limit of e. So now we really need the notion of the real exponent here, because now alpha is a real number and we need to know the meaning, what it means to take this number to this real exponent. Okay, but now that it is well defined, we can actually go on and prove this result. Okay, so the proof goes as follows. So first of all, note that this limit equals to e, and the result is straightforward, follows from the limit arithmetic theorem. Basically, we can write this expression as this quotient. So the limit in the denominator exists and equals to 1. And the limit here is actually the subsequence of the sequence 1 plus 1 over n to the power of n, for which we proved that the sequence converges to e in the previous video. So review it, if you need, if you have doubts about this result or questions. So review the relevant video. But now this sequence is a subsequence of a convergent sequence, and therefore it converges to the same limit. So the limit of the sequence is now e, and the limit of the sequence also exists, and it's 1, and 1 is not 0, obviously, and this sequence is also strictly positive. But the important thing is not 0, therefore this limit exists and equals to e. Similarly, with this expression, we can decompose it in the following way. Now it's even easier. So for this sequence, we've proved that it converges, and we denoted its limit by the letter e. And this sequence, its limit exists and equals to 1. Therefore, by the limit arithmetic theorem, just as in here, we conclude that this limit is e as well. And it's going to help us prove the following result by using the sandwich theorem. So let's see how we proceed here. So now the idea would be the following one. Suppose since alpha n converges to infinity, tends to infinity as n goes to infinity, we can find a natural number n1 such that for every n greater than n1, alpha n is going to be bigger than 1. This is some technicality, but it's important for us and we're going to use it. And so we're kind of going to assume that we're starting from now on the sequence alpha n. We're starting it from, or reviewing it from indexes that are greater than n1. Because for the purposes of limit, it doesn't matter, we can just discard any finite number of elements and it will not have effect on the limit. So now suppose that we chose this n that is greater than n1, then what we have, right, that when we take the integral value of alpha n, it's greater than 1 here. So we will at most reduce alpha n by 1. Well, basically this is valid for every x, this inequality. So it holds. This is basic inequality about integer value of any value that is greater than 0 in it. All right. So now this would imply, this is what we want alpha n to be greater than 1 here, so that we don't have to think what happens like if we take the integer value and what happens if it's 0, etc. right? So basically, if alpha n wasn't for sure bigger than 1, say it's like 0.8, then the integer value of this could be 0, right? We don't want this to happen. We don't want to think about what happens. We don't want to allow any case of dividing by 0. Therefore, we've made this assumption that it is greater than 1, and therefore the integer value of alpha n is also going to be greater than 1, and will not be dividing here by 0. And we have this inequality. Basically, it's also kind of obvious because alpha n is positive and it's bigger than 1, and it's also greater or equal to alpha n. Therefore, here the denominator is smaller than here. Therefore, this fraction is going to be bigger than this fraction, and we have this inequality. And now, if we take it to the power of alpha n, basically by the properties of the real exponents that we've proved in the previous lecture, we have this inequality. And now we're going to prove the result, derive the result based on the previous observation. So if we look at the sequence, right, then this sequence is a subsequence of this sequence, right, because those are integer values here. So this sequence is going to be a subsequence of this sequence. And as a result, since this sequence converges to E, then so does this sequence. It also has to converge to E, right? Because whenever we have a convergent sequence, every subsequence of this would be converging and to the same limit, okay? And it's important, the key property, why is this a proper subsequence? Because eventually here, we assume that alpha n tends to infinity. So, yeah, going far enough will ensure that those values get arbitrarily large, and therefore this is going to be like a proper subsequence of the sequence, right? So, and since that's since this sequence converges to E, then this sequence must converge to E as well, right? Because every subsequence of a convergent subsequence converges to the same limit. And similarly with this sequence, right? This is the subsequence of this convergent sequence. And remember, it's important alpha n tends to infinity for this to be a subsequence. And therefore, it converges to E as well, right? So we conclude that this limit by the sandwich theorem, basically we have bounded, right, if we go back here, this sequence is bounded by two sequences which are convergent to E. Therefore, by the sandwich theorem, we have is this limit exists and equals to E. Okay, good. Now we're going to prove this result, that for every real x, this limit exists and equals to e to the power of x. Okay, so for x equals 0, yeah, this is obvious. Why? Because, well, when x is 0, this value is 1, and e to the power of 0 is defined to be 1 as well. So the statement is obvious for x equals 0. Now for positive x, what we have is that x over n, if you look at the sequence, those are positive values by our assumption. So x over n are those positive values which tend to 0. Therefore, this sequence converges to infinity, right? And then by the previous proposition, now it's a sequence of real numbers. If we call by x over n, the sequence alpha n, right, or 1 over alpha n, this would be alpha n, n over x would be alpha n, then basically if we call this sequence by alpha n, then the previous result guarantees that the limit exists and converges to E, okay? Which implies, so now we are actually using this main result that was derived, even not the general form, but the result was proved in the previous lecture. Here we have a convergent subsequence of a convergent sequence that consists of strictly positive values, right? Because we assume the x is greater than 0, everything here is greater than 0, so this is always strictly positive. And the limit of this sequence, but by what we have proved, it exists and equals to E. And since this limit exists and x is this constant value, then this sequence also converges, and it converges to the value of e to the power of x. Okay, this is great. So now we only need to treat the case where x is negative, and it turns out to be quite tricky when you're doing it from scratch, okay? So yeah, we're done with this result. Now let's see what happens for negative x. So for negative x, that's a common trick. Let's denote by y to be minus x, and then y is going to be strictly positive. Okay. So now it will be apparent shortly why are we making this choice. So let us choose this natural number, and that would be the integer value of 1 plus y plus 1, and it guarantees that this n is greater than y. Okay. Then for every n that is greater than n, it is also greater than y, and we're going to apply the Bernoulli's inequality. So to what? We're going to apply it to this. Now it seems quite unclear how did I come up with this result, but just bear with me and it will become apparent. So for now, let's assume that we've made this choice. So 1 minus y squared over n squared to the power of n by Bernoulli's inequality, which was also proved in the previous lecture. So review Bernoulli's inequality and the previous lecture if it's not familiar to you. But basically, okay, the first part of the inequality, so first of all, note that n is greater than n, which is greater than y. Therefore, n is greater than y. So y squared over n squared is going to be smaller than 1. And therefore, here inside those brackets, we're going to have a strictly positive number, which is smaller than 1. And taking any natural power of that is going to leave us with a number which is strictly positive and smaller than 1. Therefore, this part of the inequality is clear. Now, what the Bernoulli inequality says, basically when this value here is greater than minus 1, like including this minus, so it's when it's right, then this is taken to the power of n is greater than 1 minus n times we have here. That's the Bernoulli inequality, and now as I'm telling it, maybe I should have quoted it in this lecture as well. But basically, Bernoulli's inequality enables us to come from here to here. Basically, this value, if we add like a plus here and minus here, then we can say that 1 plus this value is going to be greater than negative 1, is this exponent is greater than 1 minus and then n times this expression. Hopefully it was clear enough. So now let's see what we have. So first of all, now we can decompose it by this formula, right? So it's like the formula a plus b times a minus b. It's a squared minus b squared, right? So we can now decompose this product into those two products, right? And as previously it was smaller or equal to 1, this is this. And now using Bernoulli's inequality, this part is greater than this. Okay, now why am I telling you this? So choosing now n, which is greater than the maximum than this n, it ensures that this that y over n here, right, is going to be smaller than 1. So this is going to be strictly positive and it's well defined. And choosing n being bigger than y squared plus 1 also ensures that y squared over n here is going to be also smaller than 1. So we have here, what we have here is also a positive value that is smaller than 1. But the important thing is that everything here inside all the brackets is positive. So here it's positive, right, and smaller than 1. And this expression is positive, strictly positive, and smaller than 1. So now what we would like to do is to divide by this expression, right? And what we will see is that we're in no danger of dividing by 0 or dividing by something negative, which would force us to switch the direction of the inequality, because we have here, so we're now basically dividing all the sides of this inequality by 1 plus y over n to the power of n. So y is minus x, which is positive, so, and this is, so we're at no stage here are in danger of dividing by 0 or by something negative. Therefore, this inequality is well established. Everything here is strictly positive. Okay. Now, basically for 1 plus y here over n to the power of n, remember that we chose y to be minus x, and we consider the case where x is negative. Therefore, y is positive. So this limit would now, as we take the limit of n going to infinity by previously proved result, this is going to be e to the power of y. So this limit down here is going to exist. Similarly, this limit over here, and then y squared is constant. And as n goes to infinity, this limit exists and equals to 1. Therefore, applying the limit arithmetic theorem and the sandwich theorem, so this limit exists, so this limit equals to e to the power of y. And 1 over this is the definition of e to the power of minus y. And minus y equals x. So we actually proved that this limit equals to e to the power of x, even for x that is negative. Similarly here, this limit, by the same argument, this limit just exists and equals to 1. And this limit exists and equals to e to the power of e to the power of y. And therefore, by exactly the same argument, this limit is e to the negative y, which equals e to the power of x. And therefore, applying the sandwich theorem, we are applying the sandwich theorem here to this situation. So this limit converges to e to the power of x, and this converges to the power of x, where x is negative y. Therefore, what we obtain that this limit actually equals this limit because y is minus x, and it equals to the e to the power of x for x is negative. Therefore, we have proved that this limit equals e to the power of x for every real x. Okay. So we have established the main result, and now let's solve an exercise which is typical for the exercises when you study this limit about e. So let's use this famous limit to solve for this limit. Okay, so it's this similar situation, and it's a typical exercise. So let's see a straightforward and direct way to solve it. So basically, what we like to have here in the exponent, right, always, is the reciprocal of this sequence, because then by because we can see that this sequence tends to 0, right? So we want 1 over the reciprocal of this sequence. And then applying the previous result, we could say that we proved for every sequence that converges to infinity, basically the sequence alpha n would be that we want is 1 over the sequence, okay? But there's a technicality. We've proved that this limit exists. So what we want here is to have here in the exponent the reciprocal of what we have here. And basically, we're going to force it. So let's see the solution. So we're starting with this expression. Now it's not equality yet, but I'm forcing it into it. So for now, don't treat this as an equality. What I'll do is I'll take this expression and I'll write the reciprocal of this expression, because now if we had this limit, then we could state that, okay, this limit tends to infinity. Here we have this 1 over this sequence alpha n. Therefore, this limit, if we had this limit, then by the result proved, this limit exists and equals to e. Okay, but now, of course, it's not correct yet because we don't have an equality here, so I have to correct for it. And so the next step would be to correct for it. So it's still not an equality here. So we have this, right? I forced it into this, and now to correct for this, I'm taking this exponent of this expression. So now, if I apply the law of exponents, this is going to be reduced, and we get this expression to the exponent of 1. And it's still not in the exponent of 2n minus 2. So now I'm going to finalize the correction step. So I'm going to now take the exponent of all of these to the power of 2n minus 2. Now what we have here is finally a real equality. Okay, what we have now is a real equality of those expressions, and the advantage is that now we know for this internal sequence that this converges to e. Okay, so basically the important takeaway from this exercise is that whenever you have this limit of this type, you're forcing that here into the exponent you will have the reciprocal of what you have in here, and then so here you force it, and here in those two steps you are correcting for it. So now taking the law of exponents, we have this limit here to the exponent of this, okay? And regarding this sequence, we know that the sequence converges to the limit e by the result that we have already proved, which we can quote. And now we actually need to show that this sequence converges. We can see that the sequence converges to 6 over 5 by exercises we've done previously and by the limit arithmetic theorem. Therefore, what we have here is that this sequence converges to e. We will show then the sequence converges to 6 over 5. So we have here a strictly positive convergent sequence which converges to e. And here we have a sequence that converges to 6 over 5. Therefore, by the main result from the previous lecture, which we quoted here, the limit of this combined sequence exists, and it's equals to the limit of this sequence to the power of the limit of this sequence. So now let's finalize this. So this limit, if we open the brackets here, we're going to have here 6 n squared. So basically, to solve for this limit, we've done similar exercises. You need to divide by n squared on the top and on the bottom, and then to take the limit arithmetic theorem. Basically, what's important here is the ratio between the coefficients of the leading powers here, which is n squared, because other terms are negligibly small compared to n squared. But the rigorous way to go around about this is to divide by n squared and then use the limit arithmetic theorem. We have done similar exercises in this playlist before. Okay, so this limit exists and equals to 6 over 5 by the result that we have proved, right? Since this sequence converges to infinity, and this is 1 over this sequence, that we've proved that for any sequence of real number that converges to infinity, this limit exists and equals to e. So we're using this result, and now what we have, which implies, so now what we had, let's go back. So we have that the sequence of positive real numbers converges to e. This sequence converges to 6 over 5. Therefore, this limit exists and equals to e to the power of 6 over 5. And that's how you typically solve those typical exercises using the famous limit of e. You just force the exponent to be what you want it to be. Okay.